Hello everyone. Mechanical properties of fluids to hydrodynamics. In this video, I'll be talking about fluids in motion. So first, introduction. This is an example of fluids in motion, which is water coming out of a tap. At first, the flow of water through the pipe is almost steady, but as the speed of the flow increases, it becomes turbulent. Now, the study of the fluid in motion is known as fluid dynamics. And we shall see what we mean by streamline flow. Streamline flow occurs when there is a steady flow. That means when the particles of the fluid pass through a point with the same velocity in a given interval of time, then that flow is called streamline flow. Now we shall see the equation of continuity. In the case of equation of continuity, we shall consider a fluid having streamline flow. Now, for deriving the equation of continuity, we can consider three planes perpendicular to the streamline flow of the fluid at points P, R and Q. Now, let the area of cross sections be AP, AR and AQ and the corresponding velocities of the fluid be Vp, Vq and Vr. Now the mass of fluid flowing out equals the mass of fluid flowing in. That is, the mass of fluid is given by density into volume, which is rho into APVP delta T for an infinitely small time interval T is equal to delta AR VR delta T is equal to rho into AQ VQ delta T. For an incompressible fluid, the density remains the same. Hence, APVP is equal to ARVR is equal to AQVQ. Or we can say that AV is equal to constant, or the product of area of cross section and velocity of flow is a constant. Steady flow is achieved at low flow speeds. Beyond a limiting value called critical speed, this flow loses steadiness and becomes turbulent. Now we shall see Bernoulli's principle. Bernoulli's equation is a general expression that relates the pressure difference between two points in a pipe to both velocity changes and elevation changes. It is a consequence of conservation of energy. The Swiss physicist Daniel Bernoulli developed this relationship in 1738. It states that if an ideal liquid is flowing in streamline flow, then total energy, that is, sum of pressure energy, kinetic energy and potential energy per unit volume of the liquid remains constant at every cross section of the tube. That is, P plus half rho V square plus rho GH is equal to constant. We can prove this expression. For that, we have to consider a fluid flowing through a pipe having different elevations as well as cross-sectional areas. In this case, the height of the pipe at point B is h1 and that at point D is h2. The velocity of flow at B is given by v1 and the velocity of flow at D is given by v2. Now consider a infinitely small time interval delta t. During this time, the flow takes place from D to E and the volume of flow is V2 into delta T at point D and V1 delta T from B to C. The pressures at B and E are given by P1 and P2 and the areas of cross sections are A1 and A2. Now, the work done on the fluid at the left end, that is BC, is W1 is equal to P1 into A1 into V1 delta T or P1 into delta V, as we can take A1 into V1 delta T as the volume of the flow. Now the work done by the fluid at the other end DE is W2 is equal to P2A2 into V2 delta T. That's equal to P2 delta V. Now the work done on the fluid is negative P2 delta V. As the total work done on the fluid is W1 minus W2 is equal to P1 minus P2 into delta V. Now part of this work goes into changing the kinetic energy of the fluid and part goes into changing the gravitational potential energy. If the density of the fluid is rho and delta m is equal to rho into A1 into V1 delta T is equal to rho delta V is the mass passing through the pipe in time delta T, then change in gravitational potential energy is delta U is equal to rho G into delta V into H2 minus H1. Similarly, the change in kinetic energy delta K is equal to half into rho delta V into V2 square minus V1 square. Now by applying the work energy theorem, we get P1 minus P2 into delta V is equal to Pg delta V into H2 minus H1 plus half rho into delta V into V2 square minus V1 square. Now rearranging, we get P1 plus half PV1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. This is the relation between 2 points on the pipe. So we can say that P plus rho V plus rho GH is equal to a constant. Now applications of Bernoulli principle. The action of carburetor, paint gun, atomizer, etc. is based on Bernoulli's principle. That is, the main basis of working of atomizer is based on the pressure change, which produces a change in the velocity. Similarly, there is the Magnus effect. Magnus effect is the case in which a spinning ball in air gets a dynamic lift. This is caused by the drag caused by the ball when passing through the air. The top of the ball has got higher pressure than the bottom. Hence, a resultant upward lift is experienced by the ball. And this is known as Magnus effect. Then aerofoil or lift on air wing. The air wing of aeroplanes are shaped such that they cut through the air in motion such that a higher pressure is developed at the top of the wing and a lower pressure is formed at the bottom of the wing, resulting in a upward lift on the wing. Now Venturimeter. In this figure, a Venturimeter is shown. It consists of a wider cross section followed by a narrower cross section and followed by a wider cross section. And a manometer is used to measure the pressure difference between the wider cross section and the narrower cross section. We know that the velocities of the flow will be different. In the case of narrower cross section, the speed will be higher, while the velocity of the flow at the wider cross section will be lower compared to the narrower cross section. Now, the velocity at the wider cross section of the Venturimeter V1 is given by the equation root of 2 rho mgh by rho into capital A by A the whole square minus 1 the whole raised to minus 1 by 2. Here rho m is the density of the fluid in the manometer and rho is the density of the fluid. Now we can see the Torricelli's law or speed of efflux. This is also can be derived by using the equation of continuity and Bernoulli's principle. And Torricelli discovered that the speed of efflux from an open tank is given by a formula identical to that of a freely falling body, or the velocity of exit through the hole V1 is equal to root of 2gh. So this is the end of this video. If you have got any doubt in any of the topics discussed in this video, please do comment in the section below this video. Thank you.